Excellent. Everybody, thanks so much. Thanks for bearing with the last minute schedule change. I know you might be expecting to hear a talk about Baidu, but I'm going to be telling you about how you can help tune some of the algorithms that are going to be presented in that talk, which is now scheduled at 4 p.m. As was said, my name's Scott Clark, co-founder and CEO of SIGOPT. SIGOPT is a little startup up in San Francisco, a few blocks from here, that helps people do Bayesian optimization as a service. Over the course of this talk, I'm going to tell you about why you should care about Bayesian optimization, how it can help you tune your machine learning models, how it can help you get better results faster, and dive into a bunch of examples, as well as how it actually works in the underlying architecture. If you have questions throughout, please just jump up and ask them. I can just repeat them to the mic so everybody can hear, but I want to make sure I don't lose people along the way. So I'm going to start off the talk telling you two things you already know. One is machine learning is extremely powerful. You can take all of this big data and you can combine it in interesting ways to come up with really interesting insights and search and recommendations and everything like that. But tuning these systems is often extremely non-intuitive. And by this I mean the stochastic gradient descent parameters of a neural network, like in the previous talk, or the learning rates, or the topologies of a neural net, the kernels of a support vector machine. All these hyperparameters, these parameters of the model itself that are very orthogonal to the domain expertise of the person coming up with features and building these actual models. So Bayesian optimization is designed to help with this problem. And it's widely considered to be kind of an unsolved problem or a very difficult problem in machine learning. Recently, Xavier, who's the VP of engineering at Quora and used to be the director of research at Netflix, gave a question and answer session on Quora, and he classified this as the most unsolved problem in machine learning. Understanding how these deep neural nets work and then coming up with a more or less automatic way to tune them. So what I'm going to show you today is a more or less automatic way to tune them. And this is a real problem. This was released by TensorFlow a few weeks ago and was on the front page of Hacker News for a while. But this is kind of a graphical interface for tuning a simple TensorFlow model. So in this case, you can pull up a couple kind of two-dimensional data sets, build up a model, and you get to play with all these knobs and levers: learning rates, activation functions, noise, batch sizes, etc. And these are all the knobs and levers that affect how well a specific machine learning, one of these neural nets will perform. And once again, this is very non-intuitive. This is a perfect example of what a tool like Bayesian optimization can help you solve. Here we have about 22 different tunable parameters, and it's very hard to decide which one will do well. And each time you want to maybe train one of these models, it can take minutes, hours, days, or even weeks. So you need to be able to get to a good solution as quickly as possible. So there's a couple common approaches that people tend to use when they attack this problem, both in academia and in industry. So a very common approach is what's called grid search, where you take all of your different parameters and you lay out a grid, and you say, okay, I'm going to sample 10 points along learning rate and 10 points along my momentum decay and things like that, and then I'll just train a different neural net at every single one of these vertices of this grid. This grows exponentially with the number of parameters you're tuning. Sometimes this is like comboed with a random search approach. James Bergster wrote a paper somewhat recently saying that random search can actually outperform grid search for most of these deep learning problems. But it's usually one of these kind of naive approaches where you just throw a bunch of brute force at the problem. Maybe you refine. But it's very computationally expensive, very expert intensive. And once again, if it takes you an hour to train your neural net, you don't want to use one of these things because it's going to take you months or years to actually get to that best possible solution. And when accuracy matters, when that recommendation engine getting a little bit better gives you a better customer experience, when a fraud detection algorithm saves you millions of dollars, you really want to squeeze the most out of these methods. So there's a somewhat lesser known field of research that attacks this problem head on. So within the operations research community, it's called optimal learning. A lot of times it's just called Bayesian optimization, sequential model-based optimization. There's lots of different terms. But at the core, you can define it a couple of different ways. Here we have my academic family tree, trying to define it. You can think of it as, I have a time-consuming and expensive process, like training a neural net, and I want to sample it as efficiently as possible. I want to get to the best result as soon as I can, and try to do that as efficiently as possible. And I spent some time in the advertising community applying these methods, so I like to think of it as just make as much money as quickly as you can. At the high level, it's a relatively simply defined problem. I'll talk about it here at the super high level, and I'll dive into the guts of the math a little bit later after a few quick examples. But first, we want to define some objective, some overall evaluation criterion that we care about. This can be accuracy, likelihood, AUC, some combination of different metrics. But this is the number that, if it goes up, you've made a better model. And then we have the model itself. This model has these tunable parameters associated with it. The learning rates and stochastic gradient descent parameters of a neural network, the kernels and coefficients of a support vector machine, whatever it may be. This is what we can tune, and it's very expensive to try different configurations, and we want that objective to go up. So how do we get there as fast as possible? So to illustrate this, I'm going to take a super simple example here. I'm going to take this two-dimensional problem. It's non-convex, it's deterministic, which is probably not always the case with these machine learning algorithms, but we want to try to optimize this, and we want to see what some of these other approaches kind of look like. So first, we can take grid search, and grid search does exactly what it sounds like it's doing. It's just kind of blindly sampling along those indices, or those vertices of the grid. One thing worth noting here is that no information is conveyed. Like, if I sample at one point and realize that it's a poor performing point, I just blindly sample the next one anyway. I'm not really harnessing any of that very expensive information I've already gained. Random search is similar as well, where I drop a random point, maybe uniformly on that grid, and then I just drop another one and another one. At the end of the day, you look at all your results and you say, okay, what was the best I saw? But you're never really leveraging this in kind of any intelligent way along your path. Now, SIGOPT and Bayesian optimization methods in general are the complete opposite. So they're trading off exploration and exploitation. We want to take the historical information that we have and use that as intelligently as possible to make the best next step. So given what we've observed, what's the smartest thing I can do next? Or if you can run your system in parallel, what are the smartest set of things that I can do next? With the goal of having you climb this mountain as quickly as possible. So in this case, this could be learning rates and momentum decay, and this is accuracy. You want to get to that peak. That's money for your fraud algorithm. That's accuracy in your recommendation system. One thing about grid search, though, is that exponential penalty starts to really, really hurt you. So in this two-dimensional problem, maybe you're only sampling 10 by 10, that's 100. In a four-dimensional, now all of a sudden that's 10,000, hundreds of thousands. Once again, if this can take even a minute to train one of your algorithms, grid search can become impractical very, very quickly. And what we find in practice is that these Bayesian methods actually scale linearly with the data. Taking a good idea of what to do next based off of these historical points can really short circuit how long it takes to get to the best configurations of your models. So how does a system like this actually fit within a machine learning platform? So what we usually see is that there's already a platform in place. You have data scientists doing what data scientists are the best in the world at, which is taking that ugly data, cleaning it up, coming up with interesting features, really understanding the business values and metrics that you care about and what to feed into one of these models. And then you have a machine learning model itself. This could be XGBoost, this could be TensorFlow, this could be just a support vector machine, whatever it is. But there's some output that you care about. So the way that SIGOPT or another Bayesian optimization algorithm would bolt onto this would be just taking in that objective metric that you care about and suggesting optimal configurations to try next. So the goal here is to get to better models in as few of these iterations as possible. So instead of doing that exhaustive grid, you maybe only, over 10,000 points, you hit something like SIGOPT 100 times. And one thing worth noting is it doesn't bleed into the stack at all. It's just kind of clean interface on top of what you're already doing. and it just treats your underlying system like a black box to optimize. The underlying system treats this as a black box optimizer. So no matter what you've built, this can make it a little bit better. And as you continue to make your underlying systems better, this can continue to make them better yet. So they go hand in hand. So I'll show you a couple quick examples before I dive into kind of the nitty-gritty of the math of where we've applied techniques like this before and some of the results that you can kind of see, and some comparisons to standard methods. So a perfect example of this is kind of a standard classification problem. Let's say we want to take all of the loan applications from Lending Club, and we want to classify whether or not somebody's going to default on their loan or not. So we can take in things like income, credit score, loan amount. This is something where a data scientist can provide a ton of value, kind of understanding that maybe income isn't just a linear feature, like it can tail off after you make a certain amount of money and things like that. Maybe you want to combine credit score with age in a clever way, whatever it is. But once you dump it over to that machine learning algorithm, in this case we used XGBoost, which is kind of one of the standard gradient boosted packages out there, very popular in Kaggle. You want to be able to tune all of the different individual parameters: epochs, learning rate, number of trees, number of examples needed to split a node, all these kind of obfuscated parameters of that model. So you bolt SIGOPT on top, you say, I want to increase cross-validated prediction accuracy, get me to the best parameters as quickly as you can. And we can look at the trade-offs between these various approaches that people tend to take on this kind of cost versus accuracy plane. So cost down here is the number of iterations you had to try to get to a specific level of accuracy. It's worth noting that the cost graph here is on a log plot. You can think of this as your AWS bill. Accuracy, on the other hand, is your business metric. So this is how much money you lose by giving out bad loans. So you want it to be as high as possible so you can classify whether or not you should actually give that loan to somebody, but you also don't want to spend millions of dollars on AWS to get there. So once again, in this 9-dimensional problem with these kind of first-order hyperparameters that you can tune in XGBoost, it can take tens of thousands of actual iterations, even with a super coarse grid, to get to what looks like mediocre accuracy. It's worth noting that this beats the baseline, which is if you just take XGBoost and you don't tune any hyperparameters, that falls down at about 0.6 AUC. So you definitely want to do some tuning, and grid search gets you okay. Random search is a pretty good trade-off for the money, which is what was shown in that paper by Bergstra that I referenced earlier. After about 1,000 iterations, you get decent results. But then SIGOPT and these ensemble of the state-of-the-art of these Bayesian optimization algorithms is really able to beat both. And the intuition here is by leveraging every piece of data you get at every step, you can make much better decisions. So you get to higher results much faster. Typically for 5 to 10 dimensional problems, it's about 100 times faster than these other methods and better results at the end of the day. But it's not just about tuning a gradient boosted machine like this is. It can really bolt onto any system. So a lot of other applications we look at are more like classical time series analysis or regression problems. So let's say you have an algorithmic trading strategy. Instead of tuning hyperparameters like learning rates and stochastic gradient descent parameters, they're tuning things like slow and fast moving averages, thresholds for trades, weights for specific data sources, et cetera. They can take in a bunch of market data like closing prices and days of week, and the data scientists and quants that build these models really understand those features and can build it into an interesting way. And then SIGOPT bolts on top of that. So in this case, you want the highest expected revenue in as few of these time-consuming and expensive back tests as possible. So in this case, this is part of a joint blog post we did with Quantopian, which is like Kaggle for hedge funds. They do a bunch of competitions. You come up with a trading strategy. If you win their contest, you get to manage a little bit of their money. They take an ensemble of all the smartest techniques and make a lot of money on that. But what we can see is even with a simple trading strategy like we did in the blog post with them, 7 tunable parameters, the grid was so coarse in order to finish on time. There's 3 trillion different options. They were able to whittle that down to 3,000. It still lost money. The expert was able to do kind of a localized hill climbing, but once again, humans aren't really designed to do 7-dimensional non-convex stochastic optimization in their head. At best, you get to a local optima, which is what they found here. And then by applying these state-of-the-art Bayesian techniques, you can get better results. On the back test here, it beat it by 200%, 10 times faster than both that human and grid search approach. So really it's the difference between blindly marching through the space and kind of using smart math to get you there faster. And I'll talk about that smart math next. But any questions so far about, yeah, we got one here.
So if you said there are 7 trillion models, is it possible that perhaps you stumble across one model that happens to be very good and it doesn't necessarily generalize? And how do you guard against that kind of overfitting when you're doing this kind of meta?
Yeah, great question. So the question was, how do you make sure you don't overfit? And in general, this is a very important problem. One of the best things about Bayesian optimization is it's extremely efficient at optimizing any metric you give it. But that's also one of the worst things about Bayesian optimization, because if you give it a metric that will tend towards overfitting, it'll overfit better than anything else in the world. So how you usually counter that is by doing, like taking your data set, breaking it up into train test, have a holdout, doing cross-validation and regularization over that actual tuning step. And I'll go into this a little bit in some of these examples later on. But you can basically make sure that when you're tuning, you're not overfitting to the test set, and then you eventually actually run your full validation at the end against some holdout. And then the goal is whatever configuration you had, if it works in the holdout, it should extend to completely out of sample. But a lot of this falls onto the expert, because once again, in time series, this is a little bit more difficult. Depending on what your objective function actually is, you might need to take into account the fact that your data is coming from different places and things like that. But the goal here is, if you do proper cross-validation, proper regularization, if you have a metric that generalizes, then a Bayesian method will just get you to the best version of that metric very quickly. But that's an excellent question. Anybody else? Yeah. Yeah, so that's a great question. Does this only work with these types of models, or can it be extended? At the core, it's completely model agnostic. All it assumes is there's a time-consuming and expensive process that has tunable parameters. And those tunable parameters could be continuous, they can be integers, they can be categories, whatever it may be. There's some parameter space and an objective that you want to increase. And the goal is to efficiently search that parameter space to get you to the best objective. So it can be a machine learning model, it can be an algorithmic trading strategy, it could even be a physical experiment.
And what are some of the scale you have tested on for this?
Great question. So how does scale play into this? So I'll show you the math here in a second, but it does get complicated rather quickly. What we've found in production is up to a few dozen parameters, a few hundred individual suggestions, gets you to a good optima and beats kind of the thousands of suggestions that a grid search would get you to. But this is definitely designed for problems that don't have 100,000 tunable parameters or things like that. Usually, though, you can parameterize one of your problems a little bit easier than that. Like technically, if you wanted to go into the deep depths of a deep neural net, you could tune learning rates individually per node, et cetera. But most of the time, people can phrase this problem in a 6 to 12-dimensional space. Great questions. Anyone else before I dive into the math? Yeah, we got one in the back.
In the case of neural networks, how do you deal with the hyperparameter of time? Because a certain architecture will train to a high accuracy quickly. That can be a local minimum, and a different architecture will take much longer to get to a much higher accuracy.
Great question. So it's the question, if I heard it correctly, is how do you incorporate time into your objective function, or training time in particular? This is one of the nice things about these Bayesian approaches, is that the underlying objective function doesn't matter. All it needs to be is something that you can calculate. So you could take accuracy and multiply it by a time threshold. You could have some sort of penalty for exceeding 2 hours. You could have a penalty for exceeding your memory requirements. Like, it can be as ugly as you want it to be. And this method will kind of learn that boundary and be able to say, okay, this is the best method given these kind of higher level objectives that you care about, which can be a combination of anything. Great question. Anyone else? Sweet, I'll dive into the actual math here. So at the core, what this is sequential model-based optimization. The sequential is a little bit of a misnomer because you can actually get suggestions in parallel. But the idea is we want to build up some surrogate model given the history we've already observed. So if we've trained maybe a half dozen different configurations of a neural network, we want to be able to take that information in and say, how do all of these parameters interact with each other, over what length scales, how do they combine to affect this objective function we care about, and how can we use that information to extrapolate to parameter configurations that we haven't tried yet. So we need a good way to model this in surrogate where we can actually do a lot more computational techniques without having to do like gradient descent on the actual underlying system. So we use a Gaussian process to do this. I'll give you some intuition on that in a little bit. It's this very generic, very powerful framework for kind of doing stochastic regression at the high level. Once we have this surrogate model, now we want to make sure we have the best fitting one. We want to say, okay, given our regression problem, does it match the data we've seen so far extremely well? Once we have a good fitting surrogate function, now we can actually throw a bunch of other optimization techniques at it. We can say, what's the point of highest expected improvement? So given the information I've observed so far, what new configuration is going to beat the best thing I've seen so far by the most? And so this is once again trading off exploration, parts of the space that it knows nothing about, there could be good configurations out there, and exploitation, which is saying, I think I'm near a local optima. I want to make sure I resolve that and get the best value I can out of it before going back out and exploring. But there's different acquisition functions we can use here. And the idea is, given the surrogate model, make the best decision for what to try next, give that to the user, they report it back, and then repeat the process again. Now you have a little bit more information for your surrogate model, do that acquisition function again, rinse and repeat. So first up, what's a Gaussian process and what's expected improvement? So here at the top, we have a Gaussian process. There's two ways to think about this. One is that we want to model that underlying function, that underlying process that's a function of our hyperparameters as a Gaussian at every single point. So at a certain learning rate, we're expecting a certain return. That's the mean of the Gaussian, but there's some variance associated with it, some uncertainty. So every point in the space is modeled as a Gaussian. Another way to think of this is from the functional perspective, and that's saying at the beginning when we have no information, the underlying process could be represented by any function in the universe. So we have a bag, and in that bag is every function in the universe. As we start to sample points, we can throw away functions that don't make sense anymore. So if we sample a point with no noise, any function that doesn't pass through that point, throw it out of our bag. And effectively what we're doing is we're building up a distribution of functions. And that's what the Gaussian process is. The most likely function is that mean of the Gaussian process, this dashed line here at the top. But then there's uncertainty in areas where we haven't sampled. And so there's other functions nearby that we think could also be possible. So once we have this Gaussian process, as we sample more and more points, we get more and more information about what the underlying structure could potentially look like. In one dimension, this is relatively straightforward, but once again, the nice thing about these methods is they extend to these higher dimensional problems. So after a few points, we've kind of resolved the space a little bit, we've traded off a little bit of exploration and exploitation, and we can say, okay, we think this is a pretty good optima. One thing worth noting, and I'll go back to the bottom here, is that expected improvement acquisition function is the thing that we care about. This is what's telling us what's the next best thing to try. So if we have this Gaussian process here where we've only sampled this single point in the middle, maybe this is learning rate and this is some quality metric with time combined with it or something like that, we say, okay, we saw a pretty decent point here in the middle. How much do I think I can beat that point if I sample somewhere else? And that's this graph on the bottom, the expected improvement. And so in one dimension, it's really easy just to analytically plot this, but we basically want to pick optima in that expected improvement space to try. So we want points that have a relatively high mean, a little bit of uncertainty that we might be able to exploit, and we can sample there. In this case, it didn't do so well, so now the expected improvement for sampling near there has dropped way down. Now the algorithm thinks there's no way that if I sample near there again, I'm going to beat whatever is the best thing so far. So we sample over towards the left where there's still a lot of uncertainty. We do that, see a mediocre result. This is where the algorithm and the inside is kind of making that trade-off between exploration and exploitation. At the beginning, it really likes this point over here that has a lot of uncertainty on the far left. But you can see there's a point in the middle, too, that is a more exploitative point. And so as soon as we sample and reduce that uncertainty on the outside, now we want to go back in and resolve that local optima. And then we want to go back out and explore again. And it's kind of always making this intelligent trade-off. And you can see this little hump here on the left is also slowly growing. So eventually we'll exploit this reasonable space over here. And the idea is, once again, especially as this extends to higher dimensions, which makes this really difficult to plot, but it gets you to that best result as fast as possible. So now I have an extended set of examples dealing with deep learning, especially one on efficiently building convnets. But any questions about Gaussian processes, expected improvement, how Bayesian optimization works at a super high level? Yeah.
Is there an implicit assumption that the process is sequential? Like grid search, you could control all of them at once, and your exponentially goes to it?
Yeah.
Scale, and what amount can it scale to?
Great question. Does it need to be sequential? One nice thing about grid search is that you could run technically every point at once because it ignores all previous information. So there is a sequential component of this, but it doesn't need to be purely sequential. So you can get multiple suggestions at once. The intuition behind that is if I knew I could sample 3 points, if I had 3 free resources at this point and I have this information, then I can condition on the fact that I have multiple resources. And so this expected improvement graph all of a sudden is in 3 dimensions, where I get to pick, I want to find the highest sum of expected improvements. It's not quite the sum, the math works a little differently. But you basically say, given all these free resources, what can I do? And this can also work asynchronously, where you say, conditioning on the fact that I know I have a resource working on this configuration, what's the best next thing I can do with this newly free resource? And you can kind of make this trade-off back and forth. That being said, you couldn't do maybe all 1,000 points at once because then that would have no information to learn on. So there is a trade-off to be made. In practice, we usually say, don't do more parallelism than the number of parameters that you're tuning. But that gives you a decent trade-off. Any other questions? Yeah.
Do all parameters start with the same prior, or do you have a set of priors for common hyperparameters that people use?
Great question. So initially, they do all start with the same prior, but in that exploratory phase, as soon as we start to get information about that underlying space, that starts to change. So underlying all of this is kind of a covariance kernel, which is saying how much does one point influence another across every individual dimension. There's a bunch of different covariance functions you can choose. There's warping you can do to your data. There's basically a bunch of stuff to make sure that you're doing the smartest thing at every step. But at the beginning, it's mostly exploratory anyway. So if you're sampling some low discrepancy sequence, you can usually get a good amount of information once you start actually exploiting. Great question. Any other questions? Sweet. So let's dive into kind of a little bit of an extended example. The talk I'm replacing was about neural nets, so let's talk about neural nets. So let's take a common and popular tool like TensorFlow and use it on kind of a classic machine learning problem. In this case, we have a bunch of house numbers from Google Street View, and we want to be able to classify what's that house number. This is a really difficult problem. I think it's quite a bit more difficult than like the standard minced zip code data set, because you can see in some of these examples, different colors, different fonts. Sometimes there's multiple numbers in the same actual little figure. Some are blurrier than others, different angles, et cetera. If we want to attack this problem, we took an architecture from like a classic paper on this. a lot of times, these architectures themselves have lots of tunable parameters associated with them. Depths and widths, number of convolutions, size of dropout, the actual neural network itself has a stochastic gradient descent parameter in it. The previous talk was talking about different ways to do this. RMS prop and Adigrad are very popular, but they have these tunable parameters. Weight decays, step sizes, etc. And it's usually not very intuitive how you tune that architecture, let alone tune the stochastic gradient descent, let alone tune them together. Because a lot of times it's hard to intuit, here's 3 different parameterizations of RMS prop, or 9 different parameterizations of it, and they all kind of do the same thing but at different speeds, and it's difficult to intuitively say what's the best thing to try. So if we take a problem like this and we throw it at SIGOPT or these Bayesian methods, what we find is after a small number of evaluations, we're able to increase accuracy quite a bit. So the baseline for this problem would be 0.1. You just roll a d10, and whatever number comes up, that's what you classify your number as. Not tuning TensorFlow at all gets you just a little bit better than that. So if you just kind of take their default example and pipe this data set through it, it does a little bit better than random, but not much better. In fact, just throwing it at a random forest does better than that, which is this purple line here. But if we want to take one of these algorithms and actually fine-tune it because it matters to our business, it's a fraud detection algorithm or it's a recommendation system, you need to be able to do a lot better. So here we compared SIGOPT to random search. You can see that SIGOPT gets better results, faster. And this extends to that holdout data set. So that was a great question earlier. When you're actually doing this tuning phase, you need to make sure that you're doing cross-validation, et cetera. And then also keep a holdout to make sure that you're not just overfitting to some training set. So we took the best versions of all of these algorithms and threw it at the holdout training set. And you can see that, once again, TensorFlow gets you twice as good as random without tuning it, but you can do hundreds of % better by tuning it. And this really matters at the end of the day, how quickly you can get to these individual solutions. So for this specific case, we were just taking one of these small data sets from one of the Stanford libraries. And you can see that there's cost savings associated with getting to different thresholds of accuracy, even on a small data set. But once you start running things in production, and in this case with like 50 GPUs, and I know that a lot of individual companies have these big distributed GPU systems. I know Netflix has a lot of talks about how you can tune their architecture across this distributed system. You can actually get to these results quite a bit faster and cheaper, because at the end of the day, iterations are dollars on your AWS bill. Any questions about that data set? I have 2 more quick neural net examples in my 5 minutes left. Excellent. So 2 more quick examples of taking kind of the state of the art of a specific paper and being able to say, what if we go back and look at the architecture, look at all these kind of underlying assumptions, and see if we can tune it a little bit better. So for this, we're going to take a slightly different data set, CFAR 10, classifying trains, planes, and automobiles. 10 classes, once again, 0.1 is random accuracy. This is a standard problem that a lot of people compare against. There's like a leaderboard where you can see who has the best results on this. This paper was on that leaderboard very briefly, an all convolutional neural network. In this case, this was joint work with Nirvana, which is a deep learning cloud platform, where we wanted to show by using SIGOPT and their Neon neural network architecture that you're able to kind of push the state of the art a little bit further. In practice, once again, in academia and industry, the standard is brute force, grid search, make your PhD student do it, whatever it is, get to a decent result, and then publish just the parameters, not how you got there. But what we're able to see is, even in a very relatively simple system, there's lots of different parameters that are exposed. These are just kind of the high-level hyperparameters exposed within Neon, just tuning like stochastic gradient descent parameters effectively. And what we can see is, over a relatively small number of actual evaluations, SIGOPT was able to beat the published result in the paper, reducing the error rate by 1.6%. And the real takeaway here is you can get just as good as a bunch of experts fine-tuning it without having to waste expert time. So humans and data scientists in particular are incredibly good at coming up with features and creatively understanding their business propositions, but it is a waste of that expert time to make them two knobs in the dark. So you can get there or better without having to do that faster and cheaper. Another example is a deep residual net. This one stayed on the leaderboard a little bit longer. I won't go into the depth of the paper. I'll release these slides right after this and you can look it up. But basically a little bit more complicated problem. But once again, they got a decent result, 93.39%. But SIGOPT was able to reduce that relative error rate by 15% in this case, being able to get to kind of a better version of those individual parameters, getting better, squeezing better results out of these kind of state-of-the-art experts. So with that, any questions about SIGOPT, Bayesian optimization, how tools like this can fit into a pipeline? Yeah.
So what kind of GPUs were used for this? The production slide what you showed earlier.
Yeah, so that cost slide was built using just the AWS, I think it was the 4 GPU instances. Some of the work was also done on Nirvana's cloud, which uses Maxwell's instead of Kepler's, so it's a little bit faster, and they have like custom kernels that make it go a little bit faster. But in general, the idea is training on GPUs is super expensive. You want to use as few of those as possible to get to the results you care about. Yeah.
So how does this compare to other non-deterministic algorithm?
Great question. So there wasn't enough time in this talk to go over like the deep comparisons that we do. On our website, sigopt.com/research, we do some deep comparisons there. We're presenting some work at ICML next month where we compare not only against grid search and random search, but things like particle swarm optimization, as well as a lot of the open source Bayesian optimization techniques like Spearmint, HyperOpt, SMAC. I wrote Mo while I was at Yelp, which is another one of these popular libraries. And we find that we compare very favorably in terms of performance, but we also get there orders of magnitude faster just in terms of computation time because we have a big distributed system behind this API doing a lot of smart pre-computation, et cetera. And it's also a lot easier. When I wrote Mo, I tried to make it as easy as possible, but it still requires administration and a lot of time. And the goal of SIGOPT is wrap all the most powerful research in the world behind a 2-line API so you can just kind of plug and play anywhere. Yeah.
How big are the data sets you usually dealing with?
Yeah, so the underlying data set itself doesn't really matter because that's once again on the customer side. So you're feeding a big data set into a machine learning model, and all that affects is how long it takes to observe a result given a set of hyperparameter configurations. At the core, SIGOPT is designed, and these Bayesian optimization algorithms are designed to tackle time-consuming and expensive problems. But how long it takes to actually observe a configuration's performance is completely independent to the underlying set itself. That being said, the number of parameters does affect how long it takes SIGOPT or one of these Bayesian methods to perform. In practice, we usually go up to a few dozen parameters and get a few hundred suggestions, is able to get to people to a good result. What we find is usually between 10 and 20 times the dimensionality of the parameter space you're tuning, you've gotten to a good global optima. Say it one more time. Yeah, so I'll go all the way back here for a second. Yeah, so the underlying data here, for these blog posts, sometimes it's a few gigabytes. For some of our customers, it can be terabytes. The petabytes starts to get into a little bit of an issue because if it takes you weeks to evaluate a single thing, then being able to optimize within a few months or whatever matters for you, SIGOPT will do better than these standard approaches, but it can still take a long time. But it's worth noting that all SIGOPT sees is that objective metric and the parameters you tried and new parameters to come in. So this can be as big as you want. This can be as complicated as you want. This can be the combination of many different metrics. But because it's just this kind of black box optimization, it doesn't really affect us at all how long the underlying data set is. Yeah. Any other questions? Great question. So the pricing model for SIGOPT, it's a subscription-based service based off of the number of models that you tune per month. So we find that we're usually able to save people quite a bit of money off their AWS bill, regardless of the fact that it also saves data science time and like it gets you better results at the end of the day. So our kind of team-based plan gets you 50 models for $3,000 a month to cover our compute costs. And we find that teams usually recoup that very rapidly in the AWS savings.
Okay, let's give a big hand to Scott Clark of SIGOPT.
Thank you.